Hey guys, welcome back. It's Captain Hook with another problem for physics problem solving. Today we're going to move a little bit away from kinematics and actually talk about Newton's second law and creating force diagrams. We have our problem here, which again you can always see below the video. But we'll go ahead and get started because this is a 4-point thing or a 4-part thing that's going to take us a few minutes. We have a tractor with some mass connected to a trailer by a rope. The rope can carry 7,000 newtons before it breaks. So first part wants us to draw a free body diagram of the trailer before the tractor starts pulling it. We want to make sure we label all the different forces acting on the trailer and figure out what our net force is. Okay? So if we go first, we're going to draw our trailer. And we're just going to draw a nice little rectangle because it's easier. And so that's our trailer. And we know that the trailer obviously is going to be sitting on ground, probably have wheels, but we're going to ignore that and just draw a block because it's easier sitting on the ground. So we got two forces acting on the trailer. We always have gravity acting straight down. So force of gravity, which is always mg, mass times g. But it's not accelerating into the ground or flying off the ground. So we have a force holding it up, which in this case is the actual ground. It's going straight up, and that's called our normal force, which in this case, because it's not accelerating, flying into the air, flying into the ground, has to be equal to the force of gravity. So our net force there in this whole situation, since it's not accelerating in any direction, has to be the sum of those two. Well, if we consider that positive, we actually have to consider gravity going in the negative direction. So if we sum those up, obviously our net force in this case is going to be 0. So that's part 1. Okay. All right, next part, we got part 2 coming up. We now know that the tractor starts to pull the trailer with a force, we'll call it F of pull. And wants us to update our free body diagram for this situation. Okay. So what we're going to do is we're going to go ahead and redraw what we had before. Just going to draw it again. We have our trailer. We have gravity. We got the ground first, obviously. All right. But we have gravity pulling it down, which hasn't changed, still mg. We still have the normal force because it's not, again, flying into the air or anything like that. Still pulling it up, which again, still has to be mg, so they cancel out. But now, we have a force called Fpull pulling it this way. Now, I'm just saying that way. You could do the other direction if you want. I'll just say this way because usually I think about to the right as a positive x. So if we want to make it easier, let's make it whatever we do positive. Okay? But if we have it pulling, it's obviously going through the air, it's going against the ground. We're going to ignore air resistance. But we do have friction. We can't ignore that. So we have friction pulling the other direction. Okay? Now, in this case, the net force in the y direction is still 0, but it is going to start moving, start accelerating. So we know that this has to be greater than friction. Well, because one, friction can't cause motion, but it just makes sense for, obviously, if we're pulling it that direction, it's going to start moving or accelerating in that direction. So that sort of has to be the way of our larger force. Okay? So that's part 2. Part 3 now says that the acceleration of the trailer is 3 meters per second squared. It drags across the ground. We have a frictional force of 1,000 newtons acting in the direction opposite of motion, obviously. But the rope breaks. So we're going to assume that they were having just enough force to make the rope break exactly at 7,000 newtons, which is sort of its breaking maximum. So we want to know what the mass of the trailer has to be. So using this, we know that we can figure out mass. It's going to have to be that or greater. Anything greater would break it as well. Okay. So if we go back here and look, again, in the y direction, our forces still cancel out. So we know that there has to be some kind of acceleration this direction in the x direction. So in this case, we're given the acceleration in the x direction of being 3 meters per second squared. Okay. So what we're going to do is I'm going to move this out of the way for a minute. We're going to write down what we know for the x direction. We know first that Fpull has to be greater than or equal to 7,000 newtons because it breaks our rope at that point. We know that the frictional force is equal to 1,000 newtons because they gave us that. We know that our total acceleration is 3 meters per second squared. And we also, well, we need to know what the mass is. So that's what we don't know. Okay. Well, this is a simple thing. We're going to use F equals ma, force equals mass times acceleration. But in this case, it's the net force, right? Because we want the total sum, gives us our acceleration. We can figure out the mass from there, okay? So we know that net force is the sum of our individual forces, right? So in this case, we have Fpull and force due to friction, okay? Well, again, if one's positive, which we're calling Fpull positive, our frictional force has to be negative because it's always going to pull in the opposite direction. So if we actually start plugging that in, well, we can leave it like that for a second. We'll just leave F net. Well, our pull force had to be at least 7,000 newtons. And then our frictional force was obviously a negative, but a negative 1,000 newtons. So we add a negative 1,000 newtons. So our net force, we put it all together, 7,000 minus 1,000 is going to give us 6,000. 6,000 newtons, okay? But again, we know F net also equals mass times acceleration. Well, we know our acceleration, we know our force now, so we just have to solve for mass. So if we do F net equals ma, but we do a little algebra to get the acceleration over the other side, we know that mass equals our net force over our acceleration, which in this case our net force was 6,000 newtons over acceleration of 3 meters per second squared. So that gives us a mass of about 2,000 kilograms. So that's the minimum mass. So anything that or bigger would cause that rope to break. Okay. All right, our last part for this is the driver replaces the rope and tries again. Having learned his lesson, he now pulls the trailer with a resulting force of just 2,000 newtons, so it doesn't pull it as hard. However, suddenly a gust of wind pushes him directly sideways. As this happened, the driver measures the total force to be 2,500 newtons. What was the force of the wind? Okay, so this is a little bit of vector addition here. So what we need to do is we're going to just draw a little box and we'll do a force diagram for what we got. So let me get this out of the way. So again, this is for part 4. We have our trailer being pulled with a net force, I'll call it pull, of 2,000 newtons. Now this is counting friction pulling back, so this is actually the total force in the x direction. But now we have wind that came in. So our wind's going to come in. If we're going that way, it's going to do a cross sort of thing. This isn't up. This is sort of like a cross, like if the ground was underneath here. So our force of our wind is going to be this way. Okay. So we know that the sum of these two, so our total force with the wind, I'll call it F tot, is 2,500 newtons. So this goes back to some vector addition. We have to add these two together to get that. So if we redraw this real quick, and we have our force of our pull going that way, our 2,000 newtons, and we have our force of our wind going up, which we don't know what it is, and then we have our total net, which is the sum of those two coming across here. You know, that's 2,500 newtons. Well, again, we go back to Pythagorean Theorem. We know that squared plus that squared equals our total squared. So if we do a little bit, I'll put that down here. We know that 2,000 newtons squared plus F wind squared equals our 2,500 newtons squared. Do a little bit of algebra here. I'm going to subtract that to the other side and then take the square root. We know that the force due to the wind is going to be equal to 2,500 newtons squared minus 2,000 newtons squared, and we take the square root of that whole thing. And therefore our final force of our wind, which is just the part going across, is 1,500 newtons. So that's how much the wind pushed on that trailer.